Welcome to The Explainer. Today, we're diving straight into how intelligent agents tackle problems by treating them as massive search spaces. Specifically, we're looking at how they escape mazes. We're going to break down the core search algorithms in artificial intelligence that get an agent from a starting point all the way to the finish line.
So let's kick things off with a question that kind of challenges our basic intuition about navigating obstacles. Think about it. In a maze, is the shortest path always the first path found? Keep that in the back of your mind as we go, because the answer totally depends on the specific underlying logic the agent is using to explore.
Here's our agenda for today. 1. Problem solving is search. 2. Breadth-first search explained. 3. Depth-first search explained. 4. Comparing BFS and DFS. 5. Adding intelligence with A*. And 6. Visualizing the final path.
Let's start with Section 1, Problem Solving as Search, the Foundation.
Okay, so unlike us humans who can just look at a maze from a bird's eye view and instantly see all the walls and paths, an AI agent doesn't have that luxury. It has to systematically search through possible states. Basically, a state is just the agent's current position on the grid. Its actions are simply its ability to move up, down, left, or right. You've got your start state, the starting cell, and your goal state, which is the target. And of course, the obstacles are the walls. The whole problem boils down to a mathematical graph of connected open cells.
Now, I really want you to notice the concept of the frontier here. The definition is the set of generated nodes waiting to be expanded. Think of it as the boundary of what the AI has discovered but hasn't actually explored yet. Imagine you're standing in a pitch-black maze with a flashlight. The spots on the floor that your light just barely touches but you haven't stepped onto yet, that's your frontier. And how you choose to step into that frontier? Well, that defines your entire search strategy.
Moving on to Section 2, Breadth-first search explained, the methodical surveyor. Let's look at how breadth-first search, or BFS, actually works. This is what we call an uninformed or blind strategy. Its core logic is built around a first-in, first-out queue data structure. Think of this queue exactly like a line at the grocery store. The first person in line is the first person served. When BFS discovers new neighboring cells in the maze, it marks the start node as discovered, checks if it's the goal, and then enqueues all unvisited neighbors right to the back of the line. It literally won't explore those new cells until it's finished checking every single cell that was discovered before them.
Because of that queue, BFS explores the search tree level by level. It expands outward uniformly. Imagine dropping a stone into a really still pond, right? The ripples expand outward in perfect concentric circles. That's exactly how BFS works. It checks every single path of length 1, then every path of length 2. Because it never looks at a path 3 steps away before finishing all the 2-step paths, the exact second it touches the goal, boom, it mathematically guarantees that it has found the shortest possible path in an unweighted maze.
Section 3. Depth-first search explained, the bold explorer.
Now let's see how depth-first search completely flips that search behavior. If BFS is a slow, expanding ripple, DFS is like a lightning strike. Its core logic uses a stacked data structure, which is last in, first out. Picture a stack of plates in a cafeteria. You don't pull a plate from the very bottom. You take the one that was just dropped on top. So it marks the start node, and as it pushes unvisited neighbors onto the stack, it immediately pops the most recently added node to check if it's the goal. It aggressively dives right down the newest path.
Because it's constantly grabbing from the top of the stack, DFS explores one branch as deeply as physically possible before backtracking. It boldly dives down a single corridor until it hits a total dead end. Going back to our very first question, is the shortest path always found first? With DFS, absolutely not. It will run 50 steps deep down a winding path, and if it hits a wall, it just backs up one step by popping the stack and tries the very next turn. It's incredibly fast, but it doesn't care at all about finding the shortest route.
Which brings us to Section 4, Comparing BFS and DFS, the showdown.
So how do these two actually stack up? They're exploring the exact same space, but their data structures radically alter their performance. BFS uses that first-in, first-out queue, which means it has to remember the entire expanding perimeter of the search. That results in super high memory usage. It's storing thousands of nodes, but it's optimal for finding the shortest unweighted paths. DFS, on the other hand, uses the last-in, first-out stack. It only has to remember the single specific path it's currently walking down. That means radically lower memory usage, even though the path it finds is usually not optimal.
Looking at this comparison table, we can see the trade-offs really clearly. Neither BFS nor DFS uses a heuristic. BFS is optimal if step costs are equal, and it's complete in finite spaces, perfect for finding that shortest unweighted path.
DFS isn't optimal, and completeness depends on the space, but it's fantastic for low-memory exploration. So if you just need any way out of a maze, DFS is your go-to. If you need the absolutely fastest way out, you're stuck with the high memory cost of BFS. But wait, check out that third row at the bottom. A star.
Let's talk about that third contender in Section 5, adding intelligence with A star, the upgrade.
Up until now, our agent has been totally blind. It didn't know if moving left took it closer to the goal or further away. A-star changes the game by adding a heuristic, basically a really smart estimate. The magic formula here is f of n equals g of n plus h of n. The g is the actual cost from the start, which is exactly what BFS does, just counting the steps. But the h is that estimated cost to the goal. So the agent looks at its frontier, runs this simple math, and says, hey, this path looks like it gets me there cheaper. Let's explore this one first.
For a standard grid maze, we calculate that estimate using the Manhattan distance. It's super straightforward. Step 1, you find the absolute difference between your current and goal rows. Step 2, find the absolute difference for the columns. Step 3, just add those two differences together. It's like driving city blocks in Manhattan. You can only go up, down, left, or right. And because this calculation completely ignores walls, the estimate is always less than or equal to the true cost. That makes it an admissible heuristic, which is huge. It guarantees A-star will find the optimal, shortest path without endlessly searching in the wrong directions.
And finally, Section 6, visualizing the final path, the laboratory.
So once our algorithm, whether it's BFS, DFS, or A-star, finally hits that goal cell, how does it actually tell us the way out? It uses a parent map. Every single time the algorithm discovers a new cell, it records exactly where it came from, kind of like leaving a digital breadcrumb. To reconstruct the final path, we just start right at the goal, follow each node's parent backward all the way to the start, and then reverse the sequence. Boom, you've got your path.
If we visualize the maze with these colors, you really get to see the algorithm's personalities. Black is the walls, white is open, green is the start, red is the goal, and yellow is the final path. But look at the light blue, the visited or expanded cells. If you run BFS, you'll see massive amounts of light blue covering almost everything, because it searches in those wide ripples. With DFS, you'll see a jagged light blue line winding into random dead ends. But run A-star, you'll see this beautiful, tightly focused light blue stream pushing aggressively straight toward the red goal, culminating in that perfect yellow path.
To wrap up, here's a scenario to ponder. If you were navigating a massive, near-infinite maze and your computer's memory was severely limited, which search algorithm would you be forced to deploy? Based on everything we just covered about queues, stacks, and memory footprints, you've totally got the tools to answer this. Thanks for hanging out and exploring the maze of intelligent agents with me today. Keep testing those algorithms, and I'll catch you in the next explainer.